You don't need to do 126 because we didn't generate any equations in our class for 125. However, if you are here watching this, this is worth an extra stamp if you, at one point on the homework sheet, if you do copy this down and think about it. So the point of this was, if you start with this simple equation, like for example 3x plus 2 equals 11. Okay, look, if I take away 2 from both sides, I get 3x is 9, and then if I divide both sides by 3, I get that x is 3. So already I know the answer is x is 3, and that's a super simple equation to solve, right? 3 times 3 is 9 plus 2 is 11. Allows me to check it. So what if we were to make this, not so attractive? So one of the things I could do is I could, for example, choose to let's say I'm going to multiply, or I'm going to divide both sides by the number 6. So I could do this. I could write it as 3x over 6 plus 2 over 6 equals 11 divided by 6. Now I might simplify this, which would make it look a little more distorted, but I could write it as 1/2 x plus 1/3 equals 11/6, 11 over 6. And already this is not quite as clear as the original equation. However, I do want to point out that x equals 3 is still the solution to this equation. In fact, I could plug 3 in right now, and I would get the same thing. In fact, if I plug 3 in, let's do this in green, that would give me 3/2, right? Because 1/2 times 3 is 3/2, plus 1/3. And that should equal 11/6. Well, in order to add these fractions, I would multiply this by this one by 2 over 2, and I would multiply this one by 3 over 3. They both have a denominator that's 6 now. And in the first case, I've got a 9, and the other one I've got 2. Well, 9 plus 2 is 11, and this really is 11/6. So you can see, even at this point, 3 is still a solution, but I'm just making this increasingly less friendly to the person dealing with it. Kind of not demented, I guess that's the wrong word. So I could do a couple more things, but at this point I think you get the idea. This is an equation that's not as friendly as it was. Now, however, if you start with this equation and you don't see anything else around it, everything else is erased, the question is, can you reliably, consistently, and predictably get that x is 3? One of the techniques we've talked about in class is multiplying both sides by it's the least common multiple of all these denominators. And if I'm looking at these, I've got a 2 and a 3 and a 6, and the least common multiple of those is the number 6. So now that you've got this question down, the going forward solving part would be, hey, let's multiply this side by 6, and let's multiply this side by 6. And you can see when I do that, on the right hand side, it's nice, it just becomes the number 11, which reminds me of my original problem. And on the left hand side, I get 1/2 times 6, which is great, that's 3x, and then plus 6 times 1/3, which is 2. So you can see why it's nice to multiply by the least common multiple. All those fractions go away, and what was kind of a more complicated looking equation quickly straightens up, and you can see, oh, subtract 2 from both sides and then divide by 3. So question 127 asks us to solve these equations by coming up with, by first changing each equation into a simpler equivalent equation. So if in the first case, if you look at that, all three of those terms in A are divisible by 1,000. So let's divide by 1,000. 3,000 divided by 1,000 is just a 3. So I have a 3x minus 2 equals the number 10. Much easier to deal with. I add 2 to both sides. I get that 3x is 12, and I divide by 3, and we get that x is 4. So that's the solution for A. For B, if you look at that, I'm going to choose to multiply both sides of that by the number 21. So let's write this. It's negative 2x over 3 minus x over 7, and that equals the number 17. Again, I said I'm going to multiply both sides of this equation by the number 21, because 3 times 7 is 21, and that'll totally allow me to eliminate the fractions. So on the left-hand side, when I multiply 21 times negative 2x over 3, because there's a common factor of 3 in both the 21 and the 3, I can simplify that to 7 times negative 2x, or just write it as negative 14x. And I'm tempted to write all the steps. So if I could write this, I would write 2 times x, and then I might choose to write the 21 as 3 times 7, and then all over 3. This is overkill, and I would never do all of this. And then the other part I would write is 21 is 3 times 7 times x over 7. I just want to be real clear. The reason why we can do this is because there's a giant 1 in both cases, right? In the first case, the giant 1 is 3 over 3. When I simplify that, it's going to give me exactly negative 14x, and then I'm going to have minus a negative 3x, and that's going to equal 17 times 21, which is 357. And this is a total of was it 17, so negative 17x equals 357. And yes, I'm typing this into a calculator, and I'm getting that x is the number negative 21. So again, I got that by multiplying both sides by 21 to clear the fractions. For the next one, if you look at C, you can probably guess, I hope you can guess, what I'm going to multiply both sides by to clear those fractions. I've got 5 halves x minus 1/3, and that equals 13. So my denominators are 2 and a 3, and the lowest common multiple for those is 6. If that doesn't mean anything to you and you want some other way to think about it, come talk to me. We can talk about other things. But the lowest common multiple for 2 and 3 is 6. If I multiply both sides by 6, it will destroy all of these fractions. Basically, they won't even know what hit them. So let's do that. Let's multiply both sides by 6. 6 times 5 halves is just the number 15. I've got 15x. 6 times negative 1/3 is minus 2. And then 6 times 13 ends up being 78. So if I add 2 to both sides, we've got 15x equals 80, and therefore x is 80 divided by 15. And both of those can definitely be divided by, what, by 5? So if I divide both by 5, I know this is 3, and 80 divided by 5, oh, it's the number 16. So I get 16/3, and that's a nice answer. And then finally for D, you look, I've got a 10, a 5, and a 2. So I think that I'm going to multiply both sides by 10. So I have 3/10 plus 2x over 5, and that equals 1/2. So we're going to hit both sides of this with a multiple of with the lowest common multiple for 10, 5, and 2, which is 2. I'm sorry, which is 10. And you know, I've got to hit all the terms with it. So on this left side, there are 2 terms. I've got to multiply that by 10 and that by 10. I didn't point this out before. And over on the right hand side, there's just the 1 term. So on the left hand side, 3/10 times 10 is conveniently the number 3, plus 2x over 5 times 10. See, 10 divided by 5 is 2, so this is going to be plus a 4x. Think about it, try it with your calculator. And then finally that equals 1/2 times 10, which is the number 5. If I take away 3 from both sides, we get 4x is the number 2, therefore x is 2/4, and more commonly people call that the number 1/2. So x is positive 1/2. The graph at right shows a comparison of the length of several gold chain necklaces, including the clasp, to the total mass. So what we can see here is, in general, it looks like as the length increases, right, as it's a longer chain, the mass increases. And there's some variability. I mean, in general, they're going to do that, but obviously some chains may be made of, they're finer chains, or not as thick. So that's why it's not a perfect linear pattern here, but we can see this general pattern going on. And if I was to take, for example, and it says write an equation for the line of best fit. So I'm looking at this, and I'm kind of imagining there's some kind of a line that goes through here, and I don't know exactly where, but somewhere I didn't like that line. Let me try another. So it's like, as you're doing this, you're like, how do you know if you get a good line of best fit, right? Well, the point your point should kind of be distributed evenly above or below. And I don't know. I think I'm just going to go with that one. So you can see there's some points that are below that line. I'll mark them in red, and then there's some points I'll mark in green that are above that line. And usually a line of best fit tries to get kind of an equal number of each. So I don't know that this is the best, but we will definitely be learning better techniques for coming up with a very, very good description for the line of best fit. But for now, we're just kind of approximating it. And when I do this, you can see that there's apparently a y-intercept, and it looks like I've got one around +4. And another thing that I have here is there's definitely a slope triangle, and I might try and come up with a fairly good description of what that looks like. So let's say I'm going to grab this green pen, and from here I'm just going to specify some kind of a rise, and I'm actually going to go all the way up to the 28. And then from there, I'm going to go ahead and use this blue pen, and I'm going to get the run. So I'm going all the way back to my line, and I've got a run. Now, unfortunately, I don't know exactly where that's at, but it looks like it's pretty close to the number 24. So if you look at this, I've got a run of 24. It went over 24 units. And the rise shows an increase of, let's say I started at +4 and I went to 28. So that's a change of 26 units. So this slope triangle has 26 is the rise over the run of 24. And I can simplify that, right? Both of those are clearly divisible by at least 2. So I would write this as 13 over 12. So I've got a slope of about 13/12. And the other thing that I can see is I've got a y-intercept of around 4. So I might say that my line of best fit might be something like y equals 13/12 times x, and then maybe +4. And I got to be honest, right? This is not the answer. This is a answer. There's a lot of different, probably good approximations than this, and there's no right or wrong right now. I mean, there could be wrong, right? If you're telling me that the slope of that's a -5 or something, that's ridiculous, right? So, but things that are close to this, a y-intercept. If you told me the y-intercept was 12, no. If you said the y-intercept was 8, that seems kind of high. But if you're somewhere in between 6 and 0-ish, yeah. So although this is not the only answer. In fact, I've probably done this problem 4 times, and every time I come up with a slightly different equation. But you can see they all have these properties of definitely a positive slope and a y-intercept somewhere around 4. So B says, based on your equation, this is the one that I just wrote, what would you expect to be the mass of a 26-inch chain? So if I was to take x as 26 and look at the equation y equals 13/12 for a 26-inch chain, and then +4, 26 divided by 12, is that nice? Not really. It's 2 1/6. 26 divided by 12. Let me do 13 times 26 and then divide that by 12. That gives me 28 and 1/6. So y equals 28 and 1/6. And I'm going to add 4 to that. So I'm getting y is 28, 29, 30, 31, 32. About 32 and a quarter. Oh no, and a sixth, 1/6. And I can write that as, you know, some decimal equivalent. But you know, it's about 32 ounces. So, and if you look at it, you can see if I was to extend this graph this way out to 26, you know, somewhere up in here is basically a chain that has a mass of 32 grams. So that's kind of a basic look at this whole process of coming up with a least squared regression line by just kind of identifying a line that looks like it's fitting the data well, identifying the rise and the run and the y-intercept, writing the equation of the line, and then coming up with a reasonable equation. And then in this case we plugged in 26 for x to try and figure out it's a 26-inch chain. That's why that went in for x, because we were given the length of it in inches, and we think the mass should be about 32 grams. So for question 129, it says plot triangle ABC on graph paper if, and then it lists 3 coordinates. So we're going 6, 3, 2, 1, and 5, 7. So this is probably larger graph paper than I need, but I think last year it went off the screen. So let's see here. I'm going to go over 6 and up 3. This is my first point, and I'm going to label it A, and A is at 6, 3. My next point is B, and it's at x is 2, y is 1. So I go over 2 and then up 1, and then I will label this B. That's at 2, 1. And then the final point for this triangle is at C, which is at 5, 7. So I'm going to go over 5 and then way up to 7. So x is 5 and y is 7, and this is point C, and it lives at 5, 7. So I went ahead and drew the lines that connected those. The next thing we're asked to do, part B, well actually no, I haven't read part A yet, and actually these are, you can see them in your textbook, but they're down below here. So let me bring this down. Now, this is so super small. It says triangle ABC is rotated about the origin 180 degrees to become triangle A prime, B prime, C prime. Name the coordinates of the A prime, B prime, and C prime. So we're going to go 180 degrees about the origin. Well, one of the things that's nice when you go about the origin is the way these points flip. So for example, if you look at point C, it's like up 1 and over 2. So it's after I rotate 180, it's going to be from the origin down 1 and back 2. So this is the coordinates of C prime. And part of our answer is we're supposed to list that coordinate. So C prime is located at -2, 1. And the next point that we have is A prime, and if you look at A prime, it was over 6 up 5. So I'm going to go the other way with that. I'm going to go back 6. I'm sorry, it was over 6 and up 3. So I'm going to go back 6 and then down 3. So this is the location of A prime after this rotation of 180 degrees, and it's at 6, 3. Now at this point I'm doing these kind of independently of patty paper, because 180 degrees, I've seen this enough that I understand what's happening. If you're still not sure, definitely plot this point, these points, and then very carefully rotate 180 degrees. That's 290s about the origin, so you can see where the points are going. The other point, and you know, I was wrong. This actually is point B. I didn't realize that I had 2 C's above, so this is point B prime, and this point up here in the original diagram, this was supposed to be B also. So those of you that are at home like screaming like, hey, I think I fixed it now. Okay, so the final point now is C, and I'm going to follow this same this kind of pattern that I've been observing. So before, you can see it was over 5 up 7. I'm just going to make both of those negative. So I'm going to go, the opposite of 5 is going to be -5, and then a -7. So this point goes to right here. And these are the coordinates of C prime, and C prime is at -5, comma, -7. And I realize now that also, I don't know if my negative signs are erasing or if I'm not writing them, because A prime is clearly at -6, -3. So both of these should be negative. And if you already caught that, thank you. And that's what it looks like if I plot the points. Next, part B, and I guess I'm going to have to zoom out to read that. Part B says this time triangle ABC is rotated 180 degrees about point C. Oh. Okay, so before I did about the origin, now I'm going to rotate 180 degrees about point C to form triangle A double prime, B double prime, C double prime. And I remember this is why I have this large piece of graph paper, because this is what happened last year. So my point of rotation is now here at C, and I'm going to use the blue pen this time. So if I'll mark this in blue. So if I'm going to rotate, if I rotate 90 degrees about that point, I understand that X and Y's will switch places and the sign has to change. But what's going to happen here, if I look at A, if I go a whole 180 degrees, A is going to form a straight line with the line that A prime is on. In fact, if you look at this from point C, from point C I go down 1, 2, 3, 4, and then I go to the right 1. So to get the image of A, I'm going to go up 1, 2, 3, 4, and I'm going to go back 1. So that point is the location of A prime. And it is at, let's see, it's now at 4, 11. Boy, no way to really see what's happening there based on the coordinates. And then a B, when I rotate the whole thing 180 degrees, it's B prime is, oh, and this was A double prime, I'm sorry. B double prime is going to be on the same line as BC, and if I look at the slope pattern here from C to B, I would go down 1, 2, 3, 4, 5, 6, and then back 1, 2, 3. So I'm going to go up 6, 1, 2, 3, 4, 5, 6, and then I'm going to go back 1, 2, and then finally 3. So this point way up at the top here is B double prime. Okay, so the coordinates of B double prime are at 8 and 13. So X is at 8 and Y is at 13. Again, so the big observation here is that when I rotate things 180 degrees about a point, I get these lines that are showing up, and still kind of tricky, but you know, the patty paper would help kind of see this relationship. Let me draw these lines in. So you can see that B to B double prime is a straight line because of the 180 degree rotation. So there's 180 degrees there, which is a line. Same thing with A to A prime, that's a line. So kind of essentially what I'm doing is I'm just kind of extending the lines in each direction, and I'm making sure that a couple segments are congruent, right? I'm making sure that B to C, oops, I didn't want to do that. I'm making sure that B to C is congruent to C to B double prime, and I'm also making sure that A to C is congruent to C to A double prime. So these end up actually being equal. Well, they're congruent triangles because of the transformation, right? When I rotate about that point C, they end up being congruent triangles. Unfortunately, there's one more part of this. This is feeling a bit tedious. It says, finally, if triangle ABC is rotated 90 degrees clockwise about the origin, what are the coordinates of A triple prime? Alright, so last thing we're going to do now is we're going to take just our original triangle in red, and we're going to go, I forget, is it clockwise or, yeah, clockwise, like the clock goes. So that would be, you know, this direction. So we're going to end up mostly down in the lower quadrant. That's quadrant 4. And I think I've used up most of my good colors. Let's pick a, I'll go with orange. Oh, that's way too. Okay, so when we rotate things 90 degrees, either clockwise or counterclockwise, I know that the slope patterns are going to, values are going to switch. So for example, when I go to A, that was, it's like up from the origin, it's up 3 and then to the right 6 units. So if I wanted to find A, and I think we're at triple prime now, I believe I'm going to go down 6 and to the right 3. So let me go down 6 and to the right 3. So this should be the location of A triple prime. And its coordinates are at 3, comma, and then -6. So you can see it depends on if you go clockwise or counterclockwise. One of the coordinates is going to become negative because I know the slopes have to be opposites in sign and reciprocals, and the x's and y's are switching places. So that is a triple prime. Now for B, I'm going to erase this green B prime from before. So for B prime, or B rather, it says prime because there's a little purple dot from a problem or something. But B is over, it's up 1 over 2. So what I'm going to do is I'm going to go down 2. That's my negative, and then to the right 1. So this is the location of B, and then it's triple prime, and its coordinates are at, let's see, what did we say? It should be at 1, comma, and then -2. And if we could just do the same thing for C, we're going to be good. So C, from the origin, I'm going, and I'm doing it kind of as a slope triangle. That's why I'm normally, you know, the coordinates are left or right, then up or down. But as a slope triangle, from the origin, I'm going up 7 and then over 5. So I'm going to flip that. I'm going to go down 5 and then to the right 7. So to the right 7, and this should be the location of C triple prime. And again, the coordinates of that are -5 and then +7. And you can see, you know, you can see the x's and y's are clearly switching places, and also both of them before were positive, and now one of them is becoming negative. And it depends on, oh, you know, I wrote that completely wrong, didn't I? I have to be careful. I'm thinking of the slope pattern. The C is not there. C is at +7. It's over 7, and then it's down 5. So that was confusing. I'm sorry. I'm thinking of rise and run as I get that point, but I have to remember my ordered pairs are what's X and then what's Y. Totally confusing. So I think I've got that now that I've drawn it, and it's kind of cool to look at the red one to the orange one to the green one, because you see kind of this pattern as it rotates about the origin, this kind of pinwheel design. So that's our last transformation, and you can see all the coordinates there. Again, patty paper helps, but just kind of looking at it, making some observations, and just go nice and slow with it. Seems to get things done. So that's question 129. Jessica has 3 fewer candies than twice the number that Dante has. Okay. Well, that's a fact I want to try and write down here. So it says Jessica, and she has 3 fewer than twice the number that Dante has. So if I say, let's let D be the number of candies that our good friend Dante has. Looks like I wrote Dante with an H. So if D is that variable, right, then Jessica has 3 fewer than twice Dante. So this would be twice Dante, and then that's 3 fewer than him. So that's an expression that tracks how many candies she has. So if oh, look, geez, I should read this. It says if Dante has D candies, write an expression to represent how many candies Jessica has. So that's exactly 3 less than twice what he has. The next thing says, hey, if Jessica has 19 candies, write and solve an equation to determine how many candies Dante has. So if she has 19 candies, what we're looking is for these two quantities to be equal to each other. So I could say, hey, Jessica has 19. Jessica also has 3 less than twice what Dante has. So we'll add 3 to both sides, 19, 20, 21, 22. So 22 is 2D, and then finally we'll divide both sides by 2, and we get that Dante has 11 candies. So these are definitely starting out kind of simple tonight, and they'll grow over time, but the big idea that I want you to focus on right now is if bases are the same, right, then these expressions can be equal only if the exponents are equal. And we can actually go the opposite way with that too in B. In B we have the exponents are the same, so the only way that those can be equal is if the bases are the same. So if I take a look at A, right, the only way that 2 to the third can equal 2 to the x is if 3 is x, and that's so simple. Just writing that down, we've solved it. X has to be 3, and you can see when x is 3, 2 to the third is 8, and on the other side 2 to the third is 8, right? So they're equivalent. For B, the only way that x to the third can equal 5 to the third is if x is the number 5. So yes, they're this simple. Tomorrow night they're a little bit more. They ramp this up a little bit tomorrow. For C, we've got 3 to the fourth equals 3 to the 2x. Again, the only way they can be equivalent to each other is if 4 is the same exponent as 2x. So that's slightly interesting, right? So this can only be true if I solve for x here by dividing both sides by 2. This can only be true if x is the number 2. So when x is 2, these are equal to each other, right? 3 to the fourth would be equal to 3 to the 2 times 2, or 3 to the fourth power. And then the final one, D, the only way this, you can see we already have equal bases. They both have a base of 2. And the only way that this can be true is if 7 is the same thing as 2x plus 1. We take away 1 from both sides, and we get that 6 is equal to 2x. And then when I divide by 2, 3 is x, or x must equal 3. So when x is 3, this is true because both sides would become 2 to the 7th power. By the way, 2 to the 7th power is a large number. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, times 2 is 128. Is that right? 1, 2, 3, 4, 5, 6, 7. So I think it's 128. Let me do that again. 2, 4, 8, 16, 32, 64, 128. Love that. Makes me think of my computer science class.